My name is Maddie Campbell, and this is Physics 2, Lab 3. In this lab, I measured the distance dependence of a magnetic field due to a small bar magnet, and then I visualized the magnetic field using the Biot-Savart law using dPython, and lastly, I compared my measurements to my calculations for on-axis, off-axis, and 40-degree orientation. To make sure that the measurements would not be ruined, I had to make sure that there was no nearby electrical equipment. I had to make sure not to touch the magnet to my phone, and I had to properly line up my phone with north. I also had to be conscious of where I put the phone as to make sure there was no steel brackets under the table I was using. To make sure of all of these things, I worked on a hardwood floor and made sure that there were no electrical devices nearby. I used the app Teslometer on my iPhone and lined up my phone with north by making sure that the X component was 0 microteslas. By placing this north, I put the yardstick underneath to point east and west. To find the magnetometer chip in my phone, I slid the phone up and down along the meter stick until the X component was at a maximum and the Y component was at a minimum. The Z component changed very little, so we will ignore it for the rest of the lab. I then placed a piece of tape along the top of the meter stick. Next, I rotated my phone 90 degrees and repeated this process until the X was a minimum and the Y was a maximum, and placed another piece of tape. This corner where the tapes intersect is the location of the magnetometer sensor. My first measurement was finding R1000, which is the distance from the magnet to the sensor in my phone when the X component of the magnetic field is 1000 microteslas. The average distance was 0.0787 meters. Next, I placed the phone at a distance of 1.5 times R1000, which was 0.118 meters, and recorded the X component of the magnetic field 3 different times. The average of this was 0.000329667 teslas. I repeated this process for 1.75 times R1000, which was 0.137 meters. The average X component was 0.000216333 teslas. Lastly, I repeated this process for 2 times R1000, which was 0.1573 meters. The average X component was 0.000149333 teslas. All of my calculations are summarized in this Excel spreadsheet table. After calculating the average R and average B's, I then found the natural log of each one and graphed it on the graph to the right. The y-intercept is ln k, which is negative 13.876, and the slope, n, is negative 2.7412. If you look at the equation at the bottom, the n corresponds with the exponent of r. Next, I moved to dPython to visualize the magnetic field. The first line that I added was under the function def dipole b. I added the line b equals mu naught over 4 pi times 1 over r cubed times 3 u dot r hat times r hat minus mu. After calculating b, which is the magnetic field at a certain point, I added the distance 0.0786667, which is my R1000 calculated value. The next section of the code uses the dipole B function from before to graph arrows representing the magnetic field off-axis, on-axis, and at a 45-degree orientation. I calculated the X and Y components of the 45-degree arrows by using my calculated distance as the hypotenuse of a 45-45-90 triangle. After graphing all of the arrows, I printed the values of the magnetic field at each location. Lastly, I adjusted the magnet.mu value until the X component of the on-axis magnetic field was 1000 microteslas, which is consistent with my experimental measurements. I also adjusted the B scale until the arrows were a visually appropriate size. Here is my final code output along with the values of the magnetic field at each location. To test my code at the 45-degree orientation, I did it by hand using my phone and the magnet. The X and Y components were very similar, but switched. I think it may have to do with the orientation of my phone's axes. I found the percent error of the like values and found that the X component had a percent error of about 16% and the y component had a percent error of about 5%. If I had not oriented my phone to compensate for the magnetic north, then the results would have been inaccurate because the Earth's magnetic field would have been taken into account by the app too, which would have been measuring 2 magnetic fields instead of 1. And if I were to stick 2 identical magnets together end to end, the experiment would have a magnetic field that is twice as strong due to superposition.